So, we look into the problem set, and the last problem of this particular chapter is pending. The problem says a river of width t flows northwards with a speed v at a latitude theta in the northern hemisphere. Prove that the height difference h between the water levels of two banks due to Coriolis force is given by this particular expression. Now, recall that, now notice that there is a GE here. So, instead of, so this GE will come, and this GE is nothing but the corrected G value due to the centrifugal acceleration. Now, let us look into this situation. This is our earth surface. A river somewhere in this earth surface is flowing due north. So, the flow of the river is in this direction with some velocity v. Now, as the water moves due to Coriolis force, there is a acceleration or force on every water particle which is moving towards the eastern direction. Now, due to this, if I now draw the cross section of the river, how does it look? Let us say this is my river bed. Okay. Now, if this is the water level we have, okay. If there is no Coriolis force, this would have been the water level. Now, due to Coriolis force, the particles are experiencing a force which is towards east. Okay. So, this is my right. So, this will be my eastern direction, this will be the up direction, and it is moving due north. Okay. So, we are just drawing the cross section. Now, because of that, the water accumulation in the east bank of this river will be more compared to the west bank. If this happens, the river surface will have some finite tilt, although small, but there will be a tilt here, right. Let us call this angle alpha, right. Now, any particle on this surface, say, it will experience three forces. There will be one force which will be due to Fc, the Coriolis force, that will be towards east. There is a normal reaction which will be perpendicular to this surface given by n, okay, and there is a mg which is working downwards. Now, this mg and Fc, they are perpendicular to each other. Now, this g has to be replaced by ge as it is there, as it is given in the problem. Now, this ge and Fc, strictly speaking, they will not be exactly perpendicular, but this effect is so small that we can neglect that. Now, if I come back to this picture and try to show you that, okay, actually this is not, sorry. So, if I draw a perpendicular with respect to this axis, this angle here once again will be alpha. So, if I draw it once again, this part only, this is alpha and this angle is alpha, also alpha. So, this is n, this is mge, and this is Fc, right. Now, Fc is given by, for this particle of mass m, Fc is given by 2m v cross omega. Now, omega has two components, one is along east, one is along north and one is along, one is in the upward direction. Now, the component which is along north will not come into the picture, because if you recall, the velocity v essentially is towards the northern direction, and northern direction is always given by y. So, v can be written as v e y cap. Okay. So, the only component which will survive is the z component, which will be V sin theta times omega. So, this is the magnitude of the Coriolis force. For normal reaction, there will be a component which is given by n cos theta, which will be countering this mg. So, we get n cos theta or cos, sorry, not theta, sorry, this will be alpha, cos alpha. So, we have n cos alpha, which will be mge, and n sin alpha will be exactly opposing this Coriolis force, and that is why this particle, the force balance of this particle will be established. So, n sin alpha will be 2 m v omega sin theta, right. So, from this what we can do is we can write an expression for tan alpha, which is sin alpha by cos alpha. It will be given by 2 v omega sin theta by g e, right. Now, this tan alpha, now if I, so what we need to do is we need to find the height of this, we have to find this height. Now, look at this surface, look at the surface. The equation of the surface, the slope at any point of the surface is given by this. Now, if we consider this to be my, let us say, x axis and this to be my h axis. So, this tan alpha, okay, so if this is my h axis, we can also call it z axis. This tan alpha is the slope at any point, which will be given by dh dx, right. So, we get an expression just by calculating the force components. We can calculate tan alpha, which is the instantaneous slope of this surface, which will remain constant of course, but that is not strictly important, which is given by dh dx. Now, this relation, if we just integrate this relation, we get h is equal to, it is a linear relation, okay, sin theta by g e multiplied by x. So, for the maximum height, we have to put x equal to d, which is the width of the river. So, h will simply be 2 d v omega sin theta by g. So, this is the final expression which we were looking for. So, what we did here is we just calculated the, it is a very standard technique in mechanics, I think you are all familiar with it. We calculated the force components, all force components of a mass point, which is at the, on this surface of the river, and from there we have calculated the slope, and just by integrating this we get this expression. Okay. So, with this problem we officially close the discussion of this moving coordinate systems. The next topic, which is also a very important topic. So, we will start discussing system of particles, but our main aim is discussion of rigid dynamics. Now, before going into the direct details of rigid dynamics, let us define a system of particle and let us try to look into some properties of this system of particle. Now, what is a system of particle? Let us say we have a arbitrary origin. This origin is arbitrary, so we just call it some x, y, z, and we have point masses in the system. So, what is important that we know for any point mass, the mass of which is mi, this is the ith point mass, we should know the position vector r I with respect to this arbitrary origin O, right. So, ith point mass has a mass of mi and a radius vector of r I. If this is the case, then we can immediately define the radius vector or we can define the center of mass, which is given by r, which is by definition r is equal to mi R I sum divided by sum over I m I. Now, sum over I, the sum in the denominator, okay, I will just use this pen is not good. Now, total mass of the system m is given by sum over I m I. So, we can modify the definition of R as 1 over m sum over I m I R I. So, this is the definition of center of mass. So, in this system of particle we can define a center of mass with a coordinate capital R, and we can assume as if the total mass of the system is centered at this center of mass. So, with a mass capital M. So, this entire system of particle for its dynamical properties, to study the dynamical properties of this system, can be represented by a single point mass of mass capital M, which is the total mass of the system, and position vector r, which is given by this particular definition. So, this point is called center of mass or simply Cm, right. So, Cm is defined by this particular relation. Okay. So, what we are going to do is, okay, now if we look into this equation closely, we can write for continuous system, we can substitute this summation with an integration, and we can write this as 1 over r integration over the entire volume rho, or rather d m r I, where d m is the element of mass, or d m r rather, not r I, there is no I anymore. So, this is the integration, I mean the same relation written in an integration format, and this is valid for a continuous system. What is the essential difference between a discretized system and a continuous system? For a discretized system, the mass points, each of the individual mass points can be identified, and for a continuous system, a mass point cannot be identified, but what can be identified is a density term rho. Rho is the density of this system. Rho could be a constant, so it could be a constant, or rho could be a function of r. So, you can have a velocity, a density which is changing with position, or you can have a system with where the density is uniform or constant or uniform. Actually, uniform is a more accurate term for this. So, you can have an uniform density system or a density which is a function of the position. Now, if you introduce this density, then a mass element T m can be written as rho times a volume element. V is the, so what is it? Instead of the system of particle, we have a system of continuous masses, okay, where a small point mass has a mass of d m, a density of rho which is uniform across this system, and a volume of d v. So, we can replace this d m in this equation, and we can redefine r as, or I will just write it here maybe. So, we can redefine r to be equal to integration rho d v times r, and again m is nothing but rho d v, integration rho d v, and the integration is over the entire volume of the system. So, this is an alternative definition of center of mass which is equally effective. So, we are going to look into some of the examples. Okay. So, the first example will be rigid dynamics. Okay, so we'll go in here. So the first example is a rigid body consists of 3 particles of mass 2, 1 and 4 located at these 3 positions. Find the center of mass of the system. So what is given? We have some coordinate. So we know that R1 is equal to 1 minus 1 1, R2 is equal to 2 0 2, R3 is equal to minus 1 1 0, and we have mass M1 which is given by 2 units, M2 given by 1 units and M3 given by 4 units. So total mass is 4 plus 2 plus 1, which is capital M is 7 units, right, which is a summation of these 3. So R, which is the center of mass, will be the summation 1 by 7, 7 being the total mass, summation of I M I R I, right. So if we execute this, we will get so I have M1 times R1, which is, so we have to write in terms of I j k. So it will be 2 I cap minus 2 j cap plus 2 k cap. For the second mass, I just have to mass equal to 1. So I have to add 2 I cap plus 0 j cap, I am not writing it, plus 2 k cap. For the third mass, it will be, so this is a minus sign. So this is minus 4 I capped plus 4 j capped and k cap equal to 0. So I am not writing it. Okay, I will omit it. So it will be 1 over 7. Now look into I cap. We have 2 plus 2 4 minus 4. This will cancel out. For j cap, it will be minus 2 plus 4. So that means 2 j cap, and for k capped it will be 4 k capped. So R is this. The location. So if we know this, if I plot this on my x, y and z system, these points, I can also find the center of mass of this system. Now this is for problem 1. For problem 2, this is also related to center of mass. Find the center of mass of an uniform solid hemisphere of radius a. Okay. Uniform, that is a very important word. Hemisphere means half of a sphere, right. So the radius is given as a. What we can do is, we can take a slice to solve this problem. What we can do is, we can take a slice at some height h. Okay, sorry, it is not a very good drawing. I will just draw it once again. Okay, so let us say this is your hemisphere. Okay. So what I can do is, I can take a slice at a certain height. This is my origin O, and I can take at a height h or some arbitrary height z from the origin. And for this particular slice, we can assume a thickness of dz. Now the relation between this z and a being the radius, going by the triangle rule, it is z square plus r square is equal to s square, right. So, if z square plus r square is equal to if z is if dz is the thickness, then the volume dv is pi. Okay, what is r square? R square being this radius is r. Okay, so that is the total radius of this hemisphere at the bottom is a, and that is up here is r. So, r square plus z square is equal to s square. Now, dv is equal to pi r square dz, which is pi s square minus z square dz, right. Now, mass will be given by mass element will be given by dm, which is rho dv, which is rho pi s square minus z square dz, right. Okay. So, by definition of center of mass, r will be given by ratio of two integrals. The first integral is 0 to a pi rho. Now, please recall this definition. Okay. So, there is an r here. So, now what is the vector we are using here? We are using the vector, instead of r we can put z in this particular case, because we have taken this as a variable, z as the variable. So, what we can do is we can simply put pi s square minus z square times z dz, that is for the integration up, and for the lower integration we can simply integrate dv, rho dv, which is pi s square minus z square dz. Now, if you perform these integrals, you will finally get r is located at a position 3a by 8 z cap. Okay. So, I am just leaving it to you to perform this to simple integration, because in the very next step pi and rho will cancel, because rho is given to be uniform. So, is a constant. So, the integration will reduce to 0 to a being the range of maximum range of z. Okay. So, it will be s square minus z square times z dz divided by integration 0 to a s square minus z square dz. So, if you do this, finally you will get r equal to. So, z, please remember this z vector, we can simply decompose this and we can write a z cap outside. So, with this will be the final form. So, according to this result, your center of mass will be located on this line at a position which is given by 3a times divided by 8. So, which is very close to the origin. Okay. So, the center of mass is somewhere here, right. So, now we have defined, as we have defined center of mass, let us look into the some very crucial aspects of motion, which is which we can get from this, which the insight which we can gain from the center of mass picture. First of all, if we try to define, okay, so we will use a new page. So, we will see if on a system of particle, which is once again given as particles with some arbitrary origin O, r I is the position vector of the ith particle of mass m I. Now, if there is a force F I acting on the ith particle, then the total force F, which is, or F external. So, please remember this F I is an external force which is being acted on ith particle. So, total external force is a vector sum of all these forces acting on all other particles, right. So, force on this particle, that particle, that particle, that particle, everything will be included in this vector sum. Now, if this is done, then we can, and please recall that this is only the external force. There is always an internal force. So, the total force F total on ith particle is a combination of this external, I'll just write it, yeah, okay, so it's fine. So, F I plus F I j sum over j, which is not equal to I. What does it mean? The second term, see, this particle is experiencing an external force which is given by this value, but also let us say this is the jth particle which has a position vector of r j. They are interacting with each other along this particular line, right, and this force, so the force of interaction is given by F I j, right, and it's not only between this ith particle and this particle. This jth particle could be any one of the system of particle except on itself. So, the same particle cannot insert an external internal force on itself. So, j is not equal to I, but any other particle. So, for example, this one or this one or this one or this one will have an interaction with this particle, right. So, the total force is a summation of the external force plus all the internal forces due to all other particle except the self, right. So, if I execute, if I try to find out the total force on this system, which is given by F, that will have two parts. One is F external. So, I am talking about system of particle now. Please understand that there is no indices here, okay, plus F internal. Now, this F external, as we have seen, can be replaced by sum over I F I, and total internal force will be sum over I j. So, it will be this is the force only on ith particle. For all other particle, it has to be summed over I, and with this condition that j is not equal to I, it will be F I j, right. Now, what we need to understand that F I j, this particular sum will vanish. Why? Because this will come, this will give rise to terms like F I j plus F j I, right. So, F I j and F j I, according to Newton's third law, they are equal and opposite in nature. So, the combination of this will vanish, and this term, if we execute this summation, if we open up this summation and write term by term, we can always form into such pair. So, as a whole, this whole thing will not contribute, right. So, only this external, total external force that is I mean acting on this system of particle will survive, and at the end, for the entire system of particles, if we try to write the force equation for individual particle, what is the force equation? It is m I r I double dot is equal to F I. Okay. So, if I put summation on both sides, now please recall the definition of moment of inertia. What we can do is, we can center of mass, not moment of inertia, we have not come to that yet. R is equal to m I r I sum over I divided by 1 over m. So, that means r double dot is equal to this. So, if we replace that into this equation, okay. So, total, so this can be substituted by m r double dot is equal to F I sum over I F I. Now, the total force F is again sum over I F I. So, this is simply F. So, we see, as I said already, for the motion of this system of particle under a net externally applied force F, okay, or we can write it as F external itself. So, external force F is a motion as if the entire mass is concentrated at some center of mass with mass capital M and a position vector r, which is given by this relation. So, that is how we can apply Newton's law, Newton's second law for a system of particle, right. So, we will continue from here in the next class. For now, thank you.